Teleportation is a word that comes from the realm of science fiction books, and it's meant to indicate the ability for something to disappear at one place and reappear somewhere else. Now, nowadays, teleportation is no longer a science fiction world. Thanks to quantum mechanics, people can teleport information from one place to another. And the way to do that is to exploit the special properties of quantum entangled particles. Quantum entangled particles are particles that exist only in relation to each other, but they don't have an individuality of their own. This is very common. Every chemical bond in the water molecules in your body contains two electrons that have a magnetic orientation or spin that is quantum entangled. The two spins in those two electrons in the water molecules are in an opposite state, in a quantum entangled state, and they lose their own individuality. And this can be used for quantum teleportation of information. Let's see how it works. So let's say there is someone called Alice who wants to transmit a bit of information to someone else called Bob, who is at a distant location. And Alice has decided to encode physically the information she possesses onto the spin of a single electron. An electron has a magnetic orientation that can be up or down, so we could decide to call up 1 and down a 0. And Alice wants to tell Bob what binary number she has. Now, the normal way to do it would be for Alice to send an email to Bob and say, "Hey Bob, I have a 1." But that email can be intercepted, so it's not a secure way of communication. She could physically move the electron to Bob, send it through a courier, but the courier could be hijacked. So is there a way to make it absolutely secure? Yes. We can use quantum entangled particles together with the particle that carries the initial information. So let's say we have a way to create an entangled pair of electrons. These electrons are bound together, and they are in this entangled state where they are the opposite of each other. They don't have a spin of their own, but they are the opposite. Now I separate these two electrons, and I give one to Alice and one to Bob. Now, if Alice were to measure the orientation of this electron she just received, she would find it randomly either up or down. And she would know immediately that the orientation of Bob's electron is the opposite of the one she has found. But this doesn't allow her to communicate anything because the outcome of this measurement is completely random. What she really wants to do is to transmit this electron spin orientation to Bob. The way to do it now is for Alice to measure together the electron where she has the information and the other electron that comes from that entangled pair, the other half of which has gone to Bob. What Alice can now do is something very special that I will not attempt to explain. It's quite complicated. She can measure what's called the parity of these two electrons. So she's not going to try and look where each one of them is pointing. She's only going to try and see whether they point opposite or the same direction. This can be done. And let's say, for example, that she finds that these two electrons are in opposite state. Now, remember, these two were created opposite at the start. So if these two are the opposite, that means that the electron that's in Bob's hands is now the same as the original electron that Alice had in her hands. So once the outcome of this measurement is that the two electrons are opposite, then Bob's electron is instantly created to be the same as the electron that Alice had at the start. Now, this is instant. As soon as the measurement is performed, Bob's electron contains the information that was on Alice's electron. The problem is that Bob doesn't know that. This is the reason why this doesn't violate relativity. Bob can only know that this is the information that Alice used to have if Alice tells him that the outcome of her measurement was that the electrons are in opposite state. So now Alice needs to use a normal classical communication channel to tell Bob the outcome of her measurement. So for example, she could take a telephone, make a phone call to Bob and say, "Hey Bob, I found that my electrons are opposite." So then when the phone call arrives, Bob knows that this electron contains the information that used to be in Alice's hands. But the time it takes for this to happen is the time it takes to make a phone call or to send an email or to send a text message. So you need a classical communication channel alongside the creation of this entangled pair of quantum particles. And that classical communication channel works at the normal speed of light or less. Okay? Now, is it dangerous to transmit this information along this classical communication channel? I mean, of course, there could be an eavesdropper that we normally call Eve, who taps the telephone line and tries to listen to the phone call between Alice and Bob. Well, all Eve will hear is Alice telling Bob opposite, or if the electrons happen to be the same, she will say same. This is just a meaningless string of statements. From the point of view of the spy, of the eavesdropper, this string of statements, same, opposite, opposite, doesn't mean anything. It only means something when used together with the state of the electron that is in the hands of Bob. So when Bob receives this information, together with the state of the electron he has, he can reconstruct the information that Alice wanted to send him. So this is an absolutely secure way to transmit information, despite the fact that you use a normal, unsafe, classical communication channel like telephone or email to transmit some part of the information. There is another part of the information that was shared by this quantum entangled pair of particles that makes the full communication channel absolutely secure. Now, why is this called teleportation? It's called teleportation because once the protocol has run, Alice has actually lost her information. If Alice now wanted to find out, to remind herself of what was the bit of information that she had on her electron originally, she couldn't do it anymore because now this electron has been made to interact, has been entangled with the other one. And so all she will find if she tries to measure the direction of this electron is a 50-50 random up or down orientation. So she has lost her information, but the information has been teleported to the location of Bob. It's important to realize that this doesn't mean that some material object has been teleported. This electron hasn't gone anywhere. It stayed exactly where it was. It hasn't disappeared from Alice's place and appeared at Bob's place. What has disappeared and reappeared is the information encoded onto the direction of the electron. That's the thing that we teleport, is the information. This happens in the laboratory and it's being used as part of a large arsenal of technologies called quantum communications to establish new ways to transport information in a way that is guaranteed to be secure by the laws of quantum mechanics.